Organic Chemistry, Chem 213, Exam 5, Part 3. Biomolecules, amino acids, peptides, and proteins. The common amino acids. 20 amino acids form amides in proteins. They are all alpha amino acids. The amino carboxyl are connected to the same carbon. They differ by the other substituent attached to the alpha carbon, called the side chain, with H as the fourth substituent except for proline. This is a general structure for an amino acid. It's best to get in the habit of writing nitrogen on the left-hand side, the carbon with its R group at the alpha position, and then the carboxylic acid on the right-hand side. And that's because when we start combining these to build them together to make peptides and proteins, the nitrogen is always written on the left-hand side, and this carbonyl compound is always on the right-hand side. Here's examples of a few of the amino acids. Glycine, its R group is hydrogen, so it's the smallest of the amino acids. Its name is glycine, and its three-letter abbreviation is GLY. Chemists tend to use the three-letter abbreviation. There is a one-letter abbreviation tended to use more in biology, but chemists like the three-letter abbreviation because of our element symbols. We don't want to get confused with some of those. Alanine, one carbon. Phenylalanine, we have a CH2 group, then a benzene ring. And then proline is the only one that comes back upon itself. It's a five-membered ring, and it's a secondary amine, where the alpha carbon is part of a five-membered ring. Here's the abbreviation and codes for 20 amino acids. Again, chemists use the three-letter abbreviation, and biology and a lot of the other groups tend to use the single-letter code. You will be responsible to know the 20 amino acids, abbreviations, and codes. Essential amino acids. All 20 of the amino acids are necessary for protein synthesis. Humans can synthesize only 10 of the 20. The other 10 must be obtained from food. Table 26.5 in your textbook shows us the estimated essential amino acid requirements. They don't really have for infant or adults the first two, but we do have the information for infant and adult for the rest of them. You're not required to know these daily requirements. You do need to know, though, which are the essential amino acids, the ones that we must obtain by food. Compound interest, www.compoundchem.com. They have this poster on a guide to the 20 common amino acids. Chirality of amino acids. All the amino acids show chirality with the exception of glycine. It's that alpha position where we have our chiral center. Shown is the Fisher projection of some different amino acids. We also see that proteins are derived exclusively from the L amino acids. Let's take a look at the Fisher projection. L-serine, here is the alpha carbon, here's the nitrogen carboxylic acid group here. And when we have a Fisher projection, if you remember that those on the horizontal lines are actually coming out at you, so that means this hydrogen is towards you. So if we were to confirm that this is an L, let's go ahead and rank these. Nitrogen would be number 1. This would be number 2. This would be number 3. And this would be number 4. So in reviewing, establishing the stereochemistry, if you have a Fisher projection, this is what's coming out at you. So the hydrogen is supposed to be the lowest priority is supposed to be going away from you. Since it's on the horizontal, it's the opposite of what we see. We can see the order would be 1, 2, 3. It appears to be going right-handed or clockwise, but it's actually opposite of what you see, and that's why it's an L. 1, 2, 3, 4. Again, the lowest priority is on the horizontal. It's the opposite of what we see. So this would be a D. Structures of amino acids. In neutral solution, the carboxylic acid is ionized and the NH2 is protonated. This results in a dipolar ion known as a Zwitter ion. The molecule itself has both a positive and a negative charge. They are like ionic salts in solution. In an acidic solution, your Zwitter ion can undergo a protonization of this hydrogen or this oxygen here, forming an OH group. In a base solution, it's this nitrogen here that loses its hydrogen and it forms this ion. Types of side chains. 15 of the 20 amino acids are neutral. They have neutral side chains. ASP and GLU have a second carboxylic acid group, and therefore they're acidic. LSY, ARG, HIS have additional basic amino group side chains, where the N in tryptophan is a very weak base. SYS, SER, TRY, they contain OH and SH groups, and they're weak acids, and they also make great nucleophiles. Isoelectric points. In acidic solution, the carboxylate and amine are in their conjugate acid forms, an overall cation. In basic solution, the groups are in their base forms, an overall anion. In a neutral solution, both the cation and anion forms are present. This pH, where the overall charge is 0, is known as the isoelectric point, Pi. So when we're looking at Zwitter ions, when the Zwitter ion, whatever pH it is at, that's known as its isoelectric point. And you can see instead of having pH, we call it a Pi for isoelectric point. The Zwitter ion can undergo an acid reaction where the oxygen, where the anion oxygen here becomes protonated, and it has a low pH, and that means it's protonated. And then we can also have the Zwitter ion react with the base where the hydrogen, that was 3, remember the nitrogen had 3 hydrogens, where it loses 1, and it has a higher pH. We can use the isoelectric point and the fact that we can change it by either adding an acid or base to help us separate amino acids from each other. The isoelectric point depends on the side chain. 15 of the 20 amino acids have a Pi between 5 and 6.5. So a way to think about that is we know water has a pH neutral of 7. That's its isoelectric point, 7. We just call it a pH. So think about this as this is their neutral point. Instead of having like water a pH of 7 being neutral, these guys have their neutral at between 5 and 6.5. Aspartic acid and glutamic acid have an acidic side chain, and they have a lower Pi. Just like in pHs, the lower pH number was acidic. Same thing with Pi, the lower Pi number, more acidic. Histidine, arginine, and lysine have basic side chains and have a higher Pi. So this is showing us the different amino acids and how they came up with their Pi and whether or not they're acid or base, and we can do this from the pKa's of the different areas. We can use this difference in isoelectric points to separate the amino acids from each other, and this is a process known as electrophoresis. Proteins have an overall Pi that depends on the net acidity or basicity of the side chains. The differences in Pi can be used for separating proteins on a solid phase permeated with liquid. Different amino acids migrate at different rates, depending on their isoelectric point and on the pH of the aqueous buffer. So how does this stuff migrate? The one, if you have the strip at the pH of the one you're looking at, it's just going to stay the same. But if you have something that's deprotonated, its Pi is lower than that of the strip, in this case 5.97, so we have 2.77. What's going to happen is it's going to be deprotonated, and it's going to have a minus charge, and it is going to migrate to the positive electrode. Here we have a protonated species, lysine. It has a pH higher than the pH of the strip, and so it's going to be protonated. Do you see you have an overall plus charge? You have a plus here, and a minus here, so you have overall +1 charge, and it's now going to migrate to the negative electrode. So if you have an isoelectric point above the pH of the buffer, it's going to migrate to the negative electrode. If you have an isoelectric point below the pH of the buffer, it's going to be deprotonated and it's going to migrate to the positive electrode. And this is how we can separate amino acids from each other. Here we have our problem. We have a pH buffer of 8. Which electrode will each amino acid migrate towards when the pH of the buffer is 8? So we have lysine at 9.7, phenylalanine at 5.5. Which one is going to migrate to the positive electrode, and which one will migrate to the negative electrode? Go ahead and predict, pause the video, and come back and check your work. Lysine has an isoelectric point above the pH of the buffer, so it'll be protonated, and it'll migrate towards the negative end. Phenylalanine has its isoelectric point below the pH of the buffer, and it'll be partially deprotonated and migrate towards the positive end. Synthesis of amino acids. Bromination of a carboxylic acid and treatment with Br2 and PBr3. These reactions were covered in section 22.4. And then we can use ammonium or phthalimide back in section 24.6 to displace the Br. The reactive site on this molecule is going to be the alpha position. This carbon right here is going to get the bromine, and then with excess ammonia, we'll be able to convert this Br to an NH2 group, and now we have one of the amino acids. Reduction of an alpha keto acid. Here we have an alpha keto acid. We have our carboxylic acid here. At the alpha position, we have a ketone. This set of reducing agents is going to reduce our carbonyl group here at the alpha position, and we formed another amino acid. Peptides and proteins. Amino acids contain a basic amino group and an acidic carboxyl group. They're joined together in an amide bond where the NH2 of one amino acid is bonded to the carbonyl group of the next. Chains with fewer than 50 units are called peptides. Peptides are always written with the N-terminal amino acid, the one with the free nitrogen group on the left-hand side, and the carbon terminal amino acid, the free COOH group, on the right. Proteins are large chains that have structural or catalytic functions in biology. This is a general structure of amino acid with nitrogen on the left, carboxylic acid on the right. And what we see in a protein or a peptide, the chain is always going to be nitrogen, carbon, carbon, nitrogen, carbon, carbon. This is the backbone, nitrogen, carbon, carbon. And more specifically, we're going to have every second carbon, or the carbon that's next to the, and what we're also going to see is where the connection happens. Where does that amino acid end? Well, you can always tell it's between the carbonyl carbon and the nitrogen. That's where the amide bond is, or also known as a peptide bond. So this structure here, how many amino acids are represented in this structure? Well, let's count. So we have 1 here, 2 here, 3 here, 4. So this structure is showing us 4 amino acids connected. Well, how many peptide bonds are being shown? So for peptide bonds, I guess that's kind of a trick question because they have this piece cut off. But we do see 1, 2, 3 peptide bonds, and if they hadn't cut these also would have been where the location of the peptide bonds. Peptides are classified according to the number of amino acids that are linked together. When you have a dipeptide, you have 2 amino acids. A tripeptide would be 3 amino acids. A polypeptide is generally 4 or more. And then here is a contradiction. Previous it said if it had less than 50 it was known as a peptide, but now I have proteins are over 8 amino acids. So I'm not going to ask that question specifically because I've actually seen this in 2 different sources, when a peptide is called a protein and when a protein is called a peptide. So know that it's somewhere between 8 and 50. And I know that's a wide range, and my apologies for that, but I don't have a clear-cut number for that. But we do know a dipeptide, tripeptide, and polypeptide. Proteins and peptides are amino acid polymers in which the individual amino acid units called residues are linked together by amide bonds or peptide bonds. An amino group from one residue forms an amide bond with a carboxyl of a second residue. So here's an example of alanine and serine, and we're going to have individually, these are called residues. Together, it's called a peptide, in this case, a dipeptide. When you name these compounds, you always name them left to right, and the first amino acid that's there gets a YL ending. You take off the INE ending and you make it a substituent by putting a YL. And if you had more than 2 together, let's say you had a big one of like 50, all the names would have a YL ending except for the very last one on the right-hand side. It gets to be, let's call the parent. It gets to give the last name, and it gets to have the full last name here. You can see serine, the INE stays there. Now, that would be pretty long. Naming 50 of these would be pretty long. So what they like to do is the abbreviation, the 3-letter abbreviation or the code. So you would write them from left to right, and this is actually a bond line in there where we have a line between there. So this would be alanine and serine, and that's the order of that. It does make a difference because it would be a different molecule if I had serine first and then alanine. So here we have serine and alanine, where we have alanine first and serine first. These are 2 different peptides. In fact, if you have 2 different amino acids, you can get 2 different dipeptides out of that. So 2 peptides can result from the reaction of 2 different amino acids. In this case, I'm giving the example of serine and alanine. So we can see here we have the same backbone structure, nitrogen, carbon, carbon, nitrogen, carbon, carbon. What is different is the R group. We have the serine R group before the alanine R group, and in this case we have the alanine first before the serine. These are 2 different compounds, 2 different names. What are the peptides that can be made from 3 different amino acids, or how many? The easiest way to do this is to actually break it down into A, B, and C. So a lot of times when you're given this question, you'll be given the actual name of the amino acids. But let's break it down to just thinking about this logically. If you have 3 different things, how many different ways can we put these together? This is where I use this ABC method of replacing an actual structure or compound with a letter to make it simple, and then I can go back and fill in the structures afterwards. So this is how you would answer that question. You would start off with A, B, and C. That would be the first order. And then what I like to do is I like to keep the A in the front, and I switch the next 2, C and B. And then what I would do next is I put B in the front and then have A and C, keep B in the front and switch those 2. What hasn't been in the front yet is C with A and B, and then switching the A and the B, and you would get 6. So from 3 different amino acids, you get 6 tripeptides. Peptide synthesis. The number of possible permutation of amino acids and peptides where no 2 amino acids are identical is n factorial, where n is the number of different amino acids. You can see that if we had 2, where we saw earlier, 2 dipeptides can be formed, with 3 would be 6, and then it increases exponentially. So what I have part of the slide, which is actually kind of a side note, is I wanted you to see the structure of insulin. It's pretty interesting. So not only do we have the amino acids and what order they are, insulin has 2 different chains. It has an A chain of 21 units or 21 residues and a B chain of 30 units. and they're held together by two disulfide bonds. We have a disulfide bond here and here that holds this chain to this chain, another disulfide bond over here, and we have a third disulfide bond that has nothing to do with holding them together, but it actually has three disulfide bonds. And from this, we know the exact molecular structure of insulin. And we can also now say the order of the amino acids that make up insulin. Peptide synthesis. When you want a certain peptide, what you can do is you can protect one of the ends so it doesn't actually react. So you can make the actual order you want. In this case, again, we have alanine first and leucine second. Well, if we didn't protect the group, we would also get a mixture where we have alanine second. So what we can do is we can protect the nitrogen group here. We can also protect the COOH group here and form the one that we really want. After the peptide is formed, the end protected group is then removed. Covalent bonding in peptides. The amide bond that links different amino acids together in peptides is no different from any other amide bond. Amide nitrogens are non-basic because their unshared electron pair is delocalized by interaction with the carbonyl group. This overlap of the nitrogen p orbital with the pi orbitals of the carbonyl group imparts a certain amount of double bond character to the CN bond and restricts rotation around it. The amide bond therefore is planar. The NH is oriented 180 degrees to the C double bond O. Here's a graphic of what we just discussed there. You can see that there's restricted rotation and the molecule itself is planar. Disulfide bonds. We got to see these a preview when we saw insulin. And did you notice that the disulfide bond was attached to cysteine? Let's take a look. Thiols in adjacent chains can form disulfide bonds through spontaneous oxidation. A disulfide bond between cysteine residues in different peptide chains links the otherwise separate chains together, while a disulfide bond between cysteine residue in the same chain forms a loop. We can see that a molecule of cysteine has an SH group here, and this SH group here. We can lose the hydrogen and form the disulfide bond between this sulfur and this sulfur. Compound interest poster. This one had disulfide bonds in the chemistry of spider venom. If we look up in the upper right-hand corner here, we can see the disulfide bonds in the peptide being formed. And I thought this might be something interesting for you to take a look at. It also has information on proteins and enzymes. Protein classification. Simple proteins yield only amino acids on hydrolysis. Conjugated proteins, which are much more common than simple proteins, yield other compounds such as carbohydrates, fats, or nucleic acids, in addition to amino acids on hydrolysis. Fibrous proteins consist of polypeptide chains arranged side by side in long filaments. Globular proteins are coiled into compact, roughly spherical shapes. Most enzymes are globular proteins. Some common fibrous and globular proteins: collagens, elastins, keratins, those are all in the family of fibrous proteins, and they are insoluble. We can see the occurrence and use on the right-hand side of this. Globular proteins are soluble, and a couple of examples are hemoglobin and insulin. Looking more into the protein structure, primary structure of a protein is simply the amino acid sequence. What order are they in? The secondary structure of a protein describes how segments of a peptide backbone orient into a regular pattern. There are three major types of protein secondary structure. They're alpha helix, which is that coil shape that we can see over here. So there's some alpha helix through here. beta pleated, and this picture doesn't show beta pleated very well. That would be like a fan folding, and then the third one is random. So alpha helix, beta pleated, and random. Now the tertiary structure describes how the entire protein molecule coils into an overall three-dimensional shape. What can help this are those disulfide bonds we saw together that can hold different parts together. We also have hydrogen bonding, salt bridges, hydrophobic interactions. These are all tertiary features. So on this structure here, let's start off with the disulfide bonds, kind of like we saw in the insulin where it's holding this piece with this piece. This is also showing us some hydrogen bonding where these guys want to be associated with each other. There's a salt bridge here. We have a minus charge and a positive charge. And again, this will kind of hold these together. Those are all tertiary features. The quaternary structure describes how the different protein molecules come together to yield large aggregate structures. This is where the term fibrous and globular come from. And here is a structure of hemoglobin. Protein denaturization and hydrolysis. Denaturing breaks up the tertiary structure but keeps the primary structure intact. So for food, for example, with an egg, we can see that before it was cooked, we have examples of tertiary structure and it's broken up. It still retains the protein value that we need, the nutritional value, without the tertiary feature because we still have the primary there. Now, what happens though, if an enzyme is denatured, it loses all catalytic activity. Hydrolysis involves the breaking of the polymer, such as the peptides, into smaller monomers. This can only be done when water is added to each of the bonds between the monomer molecules, and the primary structure is destroyed. So denaturing breaks up the tertiary structure, primary structure retains. For food, we still get to have the protein value, but for enzymes, it loses all catalytic activity. And hydrolysis is just breaking up the whole thing. Not only is tertiary feature gone, but the primary feature is gone. Another poster from Compound Interest. This one talks about eggs, cooking eggs, the proteins, and that kind of stuff in it. So I thought you'd like to see that. And you are finished with Chem 212 and 213 lectures. Congratulations. And this is a polypeptide, I bet almost close to a protein, that spells out congratulations using the codes of the amino acids. Congratulations. Yay!